Hello there. In this lesson, we're going to learn about titration, which is a process for determining the concentration of solutions when it's unknown, using concentrations of other solutions that you do know. So let's get started. So the basis of a titration is a reaction with a known concentration of one component, like an acid, with an unknown concentration of another one, like a base. And what you can do is, if you know the volume of the acid that you used, you can work out the amount of base that must have been present. So an example here below is if you have 10 milliliters of this 0.1 molar HCl and you use it to neutralize 10 milliliters of some sodium hydroxide, since this reaction is 1-to-1, that means the sodium hydroxide must also be 0.1 moles per liter. And so, of course, it's not always going to be as even as that, but that's the basis of it. If you know the concentration of one and you know the reaction that's going on, you can work out the concentration of another. Okay, so let's have a look at some of the equipment that's used for a titration. To start off with, we have the Erlenmeyer flask, and that's the sort of triangular looking flask here, and that's where you're going to put your unknown. Well, hopefully you know what it is, but unknown concentration. That's what'll go in there. And then you have up above here a burette. A burette's a long tube that has all these gradations on it so that you can tell what volume has been used out of it. So you'll fill it up to, close to the top here. And then as you add solution, maybe it'll come down to here by the time you're done, and then you measure the difference, and that tells you the volume that was used. To hold all that stuff together, you'll need what's called a retort stand. Not sure why it's called a retort stand. It's never talked back to me. And then you've got this, burette clamp of some sort to hold the two together. The valve here at the bottom is called a stopcock. And you can turn it, either way to, allow the flow of the solution to flow, or to, cut it off. So to start off with, you're going to use a pipette to very accurately measure your volume of acid, and we're going to put that into the Erlenmeyer flask. And then we're going to add some indicator as well, so that we'll know when the reaction is complete. So the indicator we're going to use here is phenolphthalein. It's clear and colorless in an acid and goes a kind of bright fuchsia pink when it's in a base. So since acid-base titrations is the only type that we're going to be doing, there's a pretty simple relationship between the acid used and the base used when neutralization is reached. And that is that for every mole of hydrogen ion that's in the acid, it's going to need a mole of hydroxide ion in the base to neutralize it, to give you that water. So at the neutral point, the moles of those two are going to be equal, and that makes it pretty simple for us to work out concentrations of unknowns. So here's the titration equation. You'll find that it looks very similar to the dilution equation. So instead of 1s and 2s, it's A's and B's, and the A stands for acid and B stands for base, because the moles of hydrogen has to equal the moles of hydroxide, and they're both solutions, so the concentration times the volume will give you the moles. The only other thing that's added in here is that some acids have more than one hydrogen in their structure, and some bases have more than one hydroxide, and you'll have to take that into account as well. Okay, so here's our first experimental set of data. With this one, we have hydrochloric acid reacting with sodium hydroxide, and it's going to produce sodium chloride and the water. And so you can see here that there's only one H here, and there's only one OH in both the acid and the base. So concentration times acid times the volume of the acid times 1 equals the concentration of the base times the volume of the base times 1. Since they're both 1s, we don't have to worry about it hereafter. So then the concentration of the acid we don't know. We're given the volume that would have been measured at the start. We've got 25 milliliters. And the concentration of the base we are given 0.5 moles per liter. And the volume of the base is 15 milliliters. So all you need to do then is rearrange, right? So you got concentration of the acid equals 0.50 moles per liter times the 15 milliliters divided by 25 milliliters. And you can work it out to be, let's see here, 0.5 times 15 divided by 25 equals 0.3 moles per liter. Pretty straightforward. Our second reaction is a little bit different. We still have the same base, only it's the unknown this time. And this time we're titrating with an acid that has 2 hydrogens in it in order to get the neutralization to occur. So we're going to end up with sodium sulfate and water, and we'll have to balance a little bit, 2 here and 2 there. And so that's our reaction this time. So this time when we do our formula, it's concentration of acid times the volume of the acid. And this time there are 2 hydrogen ions for every 1 acid, right? H2SO4. And on the other side, we have the concentration of the base times the volume of the base. And this one only has 1 hydroxide for every 1 sodium hydroxide that is involved. So slightly more complex just because of this little 2 here. And so the math works out the same way. They'll just keep the 2 and you're good. So let's see here. Concentration of the acid is 0.5 moles per liter. The volume of the acid is 10 milliliters. And there are 2 hydrogens in that acid. And then we got the concentration of the base, which we don't know. The volume of the base, which is 25 milliliters. And there is 1 hydroxide for every mole of base. Okay, so we can rearrange this. Concentration of the base is going to be 0.5 times the 10 milliliters times the 2 hydrogens per acid divided by the 25 milliliters and the 1 hydroxide per base. And that's going to come out to 0.5 times 10 times 2 divided by 25 equals 0.4 moles per liter. Not much different, just got to keep an eye out for those acids and bases that have more than 1 hydrogen or hydroxide ion. All right, take care, see you soon.